Okay, so here's some additional energy problems I want to look at. All right, so here I have a loop, okay, which we did when we did circular motion. When we did circular motion, we looked at how fast would something have to be moving at the top of the loop so that it just barely maintains contact and fully completes the loop. Okay, so that we did. But now what I want to ask is, what height from up here would, let's say a person, let's say this is, I made this a skier, so this is frictionless, there's no friction. So what height h would this person have to start from so that at the top of the loop that they just barely maintain contact and fully complete the loop? Okay, so I think I should have demoed that last time, but if not, you can click on that link. That was a little bit better. Okay, it doesn't really complete the loop. Okay. Okay, so here it's released at a much higher point. Okay, do it one more time. And actually, you can hear that it always maintains contact. So now they have an idea of what's happening. So I'm trying to find this height such that when the skier starts from rest, all right, I want to find that height so that they just barely maintain contact and fully complete the loop. So the video we saw, okay, that showed that the skier has to go around, okay, just barely maintain contact, and we found from the previous chapters when we were in Newton's laws that meant that the normal force at the top has to be 0. Okay, and then they fully complete the loop. Okay, so for part A, okay, the person starts up here. I call that point A. All right, and everything is happening for part A up at the top of the loop. So I want to find that height. Now, when we did this in Newton's law chapter, when I did F equal ma, there's no h's in F equal ma. So that's why this is an energy problem. Now, we had our go-to energy expression, okay, about the only way the energy can change is if there's non-conservative forces that do work, all right? And I could draw the skier at other places like here, okay? So the normal force would act on them there. Here's the skier over here. Normal force would act on them there. I'll call this N1 and N2. Okay, those normal forces are different, right? But even though the normal force is a non-conservative force, it's always perpendicular to the direction that the person's headed at that instant. So the normal force does no work. So yes, there is a non-conservative force that acts on the skier, but it does no work because it's perpendicular to the direction it's going. Remember, definition of work has that cosine. And if it's 90 degrees, okay, between the direction it's going and the normal force, cosine of 90 degrees is 0. So energy is conserved. Then I'm going from point A to point P. Here's point A, there's point P. Okay, and then this up here, when it says it barely maintains contact, that means the normal force is 0. So if the person was somehow standing on a scale up here, the scale would read 0. They'd feel weightless. Okay, anything, if they start it lower here, then they wouldn't get to the top and they wouldn't fully complete the loop. Anything higher up here, they would definitely go all the way around, but the normal force wouldn't be 0. So this condition, I'm trying to find that for H. Okay, so I have E initial equals E final. So remember, energy is kinetic plus potential. And again, I'm using a capital U for potential energy. Okay, some books use PE. All right, so I'm just using a capital U. All right, so I have initial energy equal final energy. So I went down here. Okay, so my initial kinetic is 0. Okay, now initial potential, remember, you can't write down potential energy until you have a reference point. So I'm choosing the bottom as my reference point for potential energy. So initial potential energy of the skier is mg times the height h. Final kinetic is 1/2 mv squared. Okay, the final point's up here, so 1/2 mv squared. Okay, and then final potential energy is mg times the height at p. Well, their height, okay, is a radius plus another radius. So that height is 2 times the radius or the diameter. That's where that came from. Okay, and I cancel out the m's. I have an m everywhere. Divide by g. Okay, careful of the algebra. So this gives me the height. Okay, well, I don't have v, and now I need to find v. So that goes back to we did the last chapter. So I use Newton's second law. So a 5-step method of my picture. Forces, I drew forces on the skier. Normal force is 0. mg points down. Okay, pick the coordinate system. Well, actually, I'm sorry. That was my forces. So step 3, the coordinate system is based on the direction of the acceleration. So they're accelerating toward the center of the circle. Okay, nothing to break up. So I did F equal ma in the centripetal direction. So mg points down. Okay, that's my positive direction. That's mv squared over r. So mass drops out. So that gives me v. So I just need to solve it for v squared because I have a v squared here. So I take this v squared and I put it back right there. So my height is v squared, that thing is v squared, don't forget the 2g on the bottom, plus 2r. Okay, so the g's cancel, and I have, right here, I have a half. There's a half, because the 2's on the bottom, plus 2. So 2.5 is 2.5. So then that height would have to be, that height is 2.5 times the radius. So up here, I have 2r, so I'd have to go further above. So if you go back to that video, it shows here that he's releasing the ball from a height of about 2.5 up here. Okay. All right. So that was part A. So as long as this person starts from a height of 2.5 times the radius, then the normal force would be 0 at the top. Part B asks, find the force exerted on the skier by the loop at point P. Well, we already know from our analysis for part A that the force exerted on the skier by the loop, the force exerted on the skier by the loop, that's a normal force. And we already know the normal force is 0. So for part B, normal force is 0. So that's done. Okay, part C is I wanted to find, okay, again, starting from rest, okay, I wanted to find the force exerted on the skier by the loop at point Q. So I'm asking for the normal force at point Q. Okay, so Q is over here. So I redrew the picture. Okay, so if I want to find the normal force, that's a Newton's second law problem. So here's point Q, person's heading upward. So picture forces. So here's the forces that act on the skier. I have the weight downward. Okay, normal force is to the left. So the skier presses on the track to the right. Okay, that's a force on the track. Track presses back on them to the left. So remember, the normal force is a force on the skier. Okay, so I have the normal force, I have mg. So I didn't really draw an x and y because I'm trying to find n, and n is in the centripetal direction. So I'm going to apply F equal ma in the centripetal direction. So I look at my picture. The only thing that points in the centripetal direction inward is n. That's equal to mv squared over r. Now I'm trying to find n. I'm trying to find n at point Q. Well, I don't know v. How do I find v? That's an energy problem. Okay, so to find v, I do conservation of energy from where the skiers started up at the top to point Q. Okay, so again, energy is conserved because there's no non-conservative forces that do work. Okay, and this is frictionless. So here's my initial energy, final energy. Okay, so I have initial kinetic is 0 up here because they're not moving. Potential is mgh. Final kinetic energy, remember this is at point Q. Okay, so 1/2 mv squared. Okay, so I'm trying to find the speed at Q. And the potential energy at Q is mg times the height. And the height at point Q is just the radius. That's their height above the reference point. Okay, so what I did is I got rid of the m's. Okay, and then I have gh here. There's gh. Okay, and then I got v squared over 2 plus gr. I divide it, oops, what did I do here? Is I solve this for v squared. Okay, so I took this gh stays here. I brought the gr over, made it negative, and multiplied by 2. Okay, so now I have v squared, and I substitute that back right into there. Okay, so normal force right there is mv squared over r, and this is my v. So my normal force is m, there's my m, there's the r, and there's a 2, oops, I'm sorry, and then there's my v squared. So v squared is this whole thing, 2 gh minus gr. So I brought the g back, I brought the g outside, factored out the g, okay? But from part A, the height is 2.5 r. So right here where I have the h, I'm putting in 2.5 r. So that's what I did right there, 2.5 r. So 2.5 minus 1 is 1.5. And 2 times 1.5 is 3. So that says, whoops, that when the skier is at point Q, if they were standing on a scale, they would feel 3 times their weight. So normal force is 3 mg. Okay, so they feel weightless at the top. They feel 3 times their weight right there. Now, I inserted a part D. What would they feel at the bottom of the loop? Okay, so they're probably going to feel heavier. Remember, they feel weightless at the top. They feel 3 times their weight here. I want to feel, I'm going to ask, what do they feel at the very bottom? Okay, so again, when I ask, what would they feel? Okay, remember, you feel the normal force. Your body responds to the normal force. So that's a force problem. So I'm using Newton's second law. So 5-step method of my picture. Okay, I drew the forces on the skier at the bottom. Normal force points up, mg points down. Okay, they're accelerating toward the center. So that's my coordinate system. I'm applying net force centripetal equals ma centripetal. N points positive, mg points negative. Okay, again, I'm trying to find n. So I solve this for n, but I don't know the speed at the bottom. So now it's an energy problem. Okay, so I do E initial equals E final from point A up here to the bottom. Okay, so initial energy is kinetic plus potential, final energy, kinetic plus potential. Here's my reference point for potential energy. So initial kinetic 0, initial potential energy is mgh. Okay, and remember my h is 2.5 r. Remember, my h is 2.5 r. Okay, and then K final at the bottom is 1/2 mv squared. Final potential at the bottom is 0. Okay, because that's my reference point. Okay, so I have mgh is this. I can cancel out the m's and I get v squared is 2gh. But h is 2.5 r. So right here we have an h right there. I'm going to put in 2.5 r. So 2 times 2.5 is 5. So right here, where I have my v squared, I'm putting in that. So right here where I have the v squared, I'm putting that in right there. So I have n is mg plus m over r, and this v squared is 5gr. Okay, so the r's cancel, and I have mg plus 5mg, and I get 6mg. So that person would feel 6 times their weight, which is really difficult to do and not pass out. All right, so I think I had a link to this video. It shows someone driving a car around a loop. Okay, click on that. And it actually in the video, I think the driver first goes up in an airplane and feels what it's like to feel 5 and 6 times your weight. Okay, so when pilots do that in the fighter jet, they have to wear compression suits so that the blood doesn't flow from the upper body to the lower body, and they black out. So the pressure suits kind of compresses their lower extremities and keeps the blood up in the upper body so it doesn't flow out of your head. Okay, I want to add another thing. Okay, when we did projectile motion, okay, we did a problem where you shot this from the lab table, and then you had to find the speed when it hit the floor. Okay, so when we did that for projectile motion, we had the picture. Okay, this was V final. You're trying to find final velocity. Okay, your final speed. You had to draw the picture. It hits the floor. You had to break this up into its components. So you had to find V final X, which you knew because that was just V initial X. Then you had to find V final Y. Then you had to do Pythagorean theorem, okay, to find V final. All right. There's a much easier way, and that's using the concept of energy. Okay. So as the projectile flies through the air, there's no non-conservative forces that act on it, only gravity. Okay. So energy is conserved. So I'm going to write E initial equals E final from A to B. And my potential energy is 0 on the floor. Okay, initial energy equals final energy. Okay, so initial energy is kinetic, 1/f mv0 squared. Initial potential is mg times the height. Remember from the lab, that height was called y0. Final energy at the floor is just kinetic, potential 0. So I can cancel out the m's, okay, multiply both sides by 2, solve it for v final, and I get that. And I can take the square root. Okay, so when we did that lab, if we knew the concept of energy, okay, to calculate V final, we didn't have to draw a coordinate system. Okay, so when I did energy, okay, when I used energy, all this down here, I didn't need a coordinate system. Okay, I just wrote down initial energy state, final energy state, and I didn't need to draw any vectors or any forces. Okay, because the whole concept of kinematics and forces was we use that to derive the concept of energy. So anytime you can solve these type of problems using energy, it's a huge advantage. Didn't need a coordinate system, didn't need to draw any forces. All right, so I wanted to add one thing for the work chapter. Okay, so we did, let's say you have a constant force. So here's your finger, constant 10 newtons, pushes on this object. Let's say it goes 3 meters. So a constant force. So they want to find the work done by that constant force is that force times the distance to which it moves times the cosine of the angle between the applied force and the direction it's going. So in this picture, they both point to the right. So the angle between them is 0 degrees, and cosine of 0 is 1. Okay, so the work done by this force is the 10 newtons times the 3 meters gives me 30 joules. Now, if I plot it force versus position, F versus X, force is a constant. Okay, so it's 10 newtons, so it's a constant 10 newtons. So we found the work done by that force is 30 joules. Well, that side is a height of 10, and that side is a length of 3 meters. Okay, so 30 joules looks like I did 10 times 3. It looks like I'm finding the area under that line. Okay, so to find the work done by constant force, it's the area under that line. So we can extend that now to variable forces. Okay, so we'll do springs in a much later chapter, but they mention the concept of the work done by variable force. And in the projectile lab, you put the plunger in and you press the ball back, and you found that the farther you had to compress the ball, the larger force you had to apply. So the spring force is a variable force. It's a function of how far you want to compress it. Okay. So let's say the spring force, or let's say a force, okay, if I plot the force versus how far I'm going to compress it or stretch it, okay, that's no longer a constant, it's a curve. Okay, so to find the work done by that force, it's still the area under that curve. Okay, and I put this as an aside. Aside means don't worry about it, you could ignore it. But from, whoops, what happened there? From a calculus class, okay, from a calculus class, the the area under the curve is represented by an integral. Okay, don't worry about that. So this chapter, they talked about the work done by a variable force. If they give you a graph, like maybe if they give you this is force and that's distance, okay, and that's the shape of it, you could find the work done because, the work done is the area under that. You know how to find the area of a triangle, just 1/2 the base times the height. Here I have Tarzan. Give me the weight of Tarzan standing on the cliff, okay, holding a vine, and they give me the height that they fall through, okay, and I want to know, will the vine break? And they tell me the vine will break at that tension, all right? And then I had to add that, assume that he starts from rest here at the cliff and swings down to here. Okay, so we have to figure out where is the tension going to be the biggest to figure out whether or not the vine's going to break. Okay, where is the tension the biggest? Well, we could probably argue the tension is probably biggest at the bottom as he swings back and forth. So what I did is I just chose some arbitrary place, like over here, and I drew him swinging at that spot. Okay, so Tarzan is right there, right? And I want to find the tension, so that's a 5-step method. So I need to calculate the tension, okay, at that spot. So I do my forces on Tarzan, so I have the tension in the string, and I have his weight. Okay, so my picture, my forces, coordinate system. Well, the coordinate system is based on the direction of acceleration, and he's accelerating toward the center of the circle. That's the direction of my acceleration. So that dictates my coordinate system. Here's my x-axis, there's my y-axis. All right, so that says I had to break up mg. So if this is the angle theta, that's my angle theta. So this is mg cosine, that's mg sine. And I put 2 lines through that to remind myself I've broken it up. Okay, and then I apply F equal ma in the centripetal direction. So I have t points inward, mg cosine points away, and that's equal to mb squared over L, because he's moving in a circle of radius L. So L is the length of the vine. Okay, so I solved this for t. All right, so this is the tension at any place when he's swinging. So I have to figure out where's the tension the biggest. Okay, so I have to figure out what value. Okay, well, what are the constants? So mass is a constant, g is a constant, length of the vine is a constant. So the only variables are theta and v. Okay, well, the biggest that cosine theta gets is 1. Okay, so that's the biggest when theta is 0 degrees. Cosine 0 is 1. So that's at the bottom. Okay, when he's at the very bottom here. Okay, so that makes cosine theta the biggest. All right. Well, where is the speed the biggest? All right. Well, as it turns out, the speed is the biggest also at the bottom. Okay. Now let's argue why that is. So let's say he starts here, and he's swinging back and forth. So he's at rest here, and he's at rest here. All right. So with respect to where he started, all the energy is potential here, gravitational potential energy here. Then it's all kinetic here. It's all potential when he comes up to this height, comes back here, all kinetic, all potential, all kinetic, all potential. Okay, so all of the energy, okay, is kinetic at the bottom. So that means his speed is the biggest at the bottom. All right, and we already looked at springs a little bit, so I kind of projected this image down. Look at a mass on a spring, and we'll see in the future when we get to chapter 15 that if this spring oscillates between these 2 points, okay, the mass is at rest on the ends, okay, just like we already did. We did Hooke's law spring force. So if it's at rest at the end, that means it has to pass through a maximum at the middle, and that's what Tarzan's doing. Okay, so the speed is the biggest at the bottom. So that says that the tension is the biggest at the bottom. So I redrew the same picture. Oops. But now I put him at the bottom. Okay, so here's Tarzan at the bottom, and I want to find that speed at the bottom. I want to find the tension first at the bottom. So picture, forces, coordinate system. Okay, coordinate system is based on the acceleration. So here I'm not drawing x and y. I'm just doing this in the centripetal direction. I don't need the x direction. So I have t points up, mg points down, and that's equal to mv squared over L, where L is the radius of the circle. So this gives me the tension. And if I compare this one to this one, okay, this is what I have. Because up here I had mg cosine theta. Well, you're at 0 degrees, so cosine theta is 1. Okay, there's my 1. And I have mv squared over L. So mv squared over L. So this is the tension at the bottom. All right. So I need to find V. Okay. Now that becomes an energy problem. So I use our go-to energy expression. Okay. Where this term energy lost is the energy loss due to kinetic friction. Well, there's no kinetic friction. That term's 0. Okay. So I have to look at this term. Work done by non-conservative forces. Okay. Are there any non-conservative forces that act on Tarzan? Yeah, the tension. That's a non-conservative force. There is no potential energy function associated with the tension. Well, as he swings back and forth, okay, the tension is always perpendicular to the direction he's going. So the tension force is always perpendicular to the direction he's headed at that instant. Okay, so even though there is a non-conservative force, it does no work. So that term is now 0. So therefore, energy doesn't change. Okay, so final minus initial is 0. So that says energy is conserved. So I redrew the same picture. Here's where we started on the cliff. So I'm going from A to B. So I wrote each energy term, potential plus kinetic. So here's my reference point at the lowest point. So initial potential energy is mgh. Kinetic 0, because start from rest. Final potential is 0 at the bottom. Final kinetic at the bottom is my 1/2 mv squared. Okay, mass of Tarzan drops out. So that gives me speed squared at the bottom. The reason I left it as speed squared is because I needed to pop it in to the tension. So I'm putting in for v squared right there. Okay, and then I factored out mg. All right, and then I looked up above and I got the weight of Tarzan. That's the height. Okay, the length of the vine is 15 meters. So this gives me the tension of the vine at the bottom. But in the problem, okay, the maximum tension, was 1112. So we found that the tension of the bottom is 1077, which is less than the breaking strength of the vine. Therefore, the vine doesn't break.